Hey, for the first time in class history, I remembered to hit the record button. For whatever reason, 10 a.m. Record every time. This one I've got to yoink it off of Twitch. So, let's get started here. Is everybody doing okay with the homework? So, if you forgot, it is due tonight at midnight. 10 out of 10, yeah, that's good stuff to listen to if you're trying to get your day going. Um, when I'm trying to focus, I tend to I think it's the post-rock genre. So, where's it at? There we go. Pelican, explosions in the sky, God is an astronaut. That's my focus jam. May have forgot the homework. It's due tonight. You still have plenty of time. Oh, clearing cookies, yeah, so that's probably how it tracks what's done and what's not done. But yep. Yep. It's hey, whatever helps you focus, right? So homework is due tonight. Don't clear your cookies. There you go. Good suggestion there. If I can get somebody to stop me at 140, because I will probably ramble on today. That's just how I roll. I want to go over GitHub and how to fork and clone repos and things of that nature with you and how I'm going to be doing it. Got you. Awesome. Because it's going to be very important for your upcoming homework assignment. So you have the thing due today. I'm actually using Windows. Um, this is more interesting than the material probably, for me anyway. I'm using Windows 10. I've installed a custom start menu, and I use Ubuntu on Windows. So I prefer Ubuntu, but I have lots of stuff in Windows that it's annoying to use something like Wine or what is it, Crossover. I like playing Steam games or um, Adobe products don't work too well in Linux. So basically, this is the solution to all my prayers. Ubuntu on Windows is awesome, and I love it. It is basically what Sigewin should be, honestly. Sigewin can be a huge pain in the butt too. So yeah, we are going to go over main software engineering topics today, and I'm hoping we don't get any more trolls in chat today because otherwise I have to spend time muting people and later banning them, unless any of my other people catch that. But it's going to be fairly dry, just to warn you. Um, we've got a slightly different aspect ratio, meaning I'm using somebody else's slides. I try to avoid doing that, honestly, but these ones they're pretty comprehensive, honestly. These are good. I've got a few of these. They're good as a reference for later on. And squishing this into widescreen format just makes it actually look awful. So yeah, we are going to do a Git demo because your homework is going to be getting up and going with Git and GitHub, getting your project teams all sorted out, and getting an initial proposal up and running. You're going to have more time than like 3 or 4 days. I'll give you probably like a week and a half or 2 weeks or something like that to get it done. So there's a little bit more meat to it, but it's a bigger part of your project. So going to be important for me to show you what's going on. And your lab manual is nearly there, but I'm going to have like a walkthrough for how you're going to get some basic things up and running. Only caveat is that with everybody having different machines, Linux, Windows, Mac, Raspberry Pi with a screen attached, but you can install and run Git on any machine, honestly. So tools are going to be different between all of them. I'm going to show you how I do it through the terminal. So I'll have a demo of that. What we're going to cover today, though, is basically the things you need to know about what software engineering actually is. All right, so I'm going to skip through. So there's some of the case studies we've already talked about. I'm going to skip those in these slides, and I'm probably going to skip through some of the more boring ones as well. Boring, repetitive ones, maybe. We've covered everything so far that is catastrophic, all the ways that software can go wrong. Now we're going to actually be talking about how software can go right and how we can actually have a process to make sure that we create good software projects, right? So the process is what we are going to be going over today, and the different types of processes we'll talk about next time. So that is about where we're at. And then you can all go and have a wonderful weekend, I hope. So we're going to talk about today what software engineering actually is, how we are doing as a domain, and what a typical process would be, and our track record basically. So let's start off with what a software project or product actually is. They are very large and very complicated, depending on what kind of a project you're making, whether it's a phone app or a web application with RESTful APIs, or you're making a terminal application or a bash script. I mean, it doesn't matter. Software is going to be complicated at some level of abstraction. To create these programs, we need both analysis and synthesis. So analyzing, I'll go right to the figure here, and I should warn you, there is a clip art warning for these slides. This Flagger and Atlee, these are two very well-known people in software engineering now that my Google bar is covering that up. But they like their clip art, which is fine. It looks great. But in software, typically we're trying to solve some kind of a problem, right? Your customer is going to come to you, or you're going to come up with some kind of a problem that you need to solve. Whether you want to make your job easier to automate something, or you want to create, a phone app that's going to be fun or helpful, or whatever it is. There is something to do, and software is a great way to solve that, right? The trick is that software is made up of many, many pieces, many, many problems you're trying to solve. So a good example is like a web application where you have different components, or maybe let's talk about it in terms of a phone app. Your user interface is just one problem, right? If it is something where you have different buttons that you want easier to click, okay, how do we lay out the buttons? What do those buttons do? Do we have to verify that the user clicked a correct sequence of buttons? Do we have to validate whatever the user is putting in or what's coming out of our internal database? So there's a lot of little subproblems. What analysis and software engineering is decomposing a problem into manageable chunks so that you or your team can manage them. And then synthesis, excuse me, synthesis is where we take a number of possible, hopefully feasible solutions and stitch them together to make one kind of global solution. So here, let's say solution 1, this is going to solve our user registration. Solutions 2 and 3 might go into data validation, making sure that what you're putting in your phone isn't necessarily hurting the rest of the ecosystem or snooping. We talked about privacy last time. So stitching all these together, hopefully we'll go back to solving this problem that we created. So I've got some formal terms here for you, and these are more good for you to know in terms of software engineering. And again, I apologize because it's kind of not the easiest, I guess, to read. It's more of a blast of information. Don't do this when you go to do your project presentations. But basically, we're going to have methods, which is just some kind of a procedure to solve a problem. You'll have tools to help you. You'll have procedures for using those tools with your method to create your product. But kind of the important thing here is this paradigm. How are you developing your software? Are you going object-oriented? Are you going functional? Are you following the waterfall process versus agile versus spiral? So with paradigm, it's important that everybody is on board, right? So that you're all having a unified effort in terms of development. Okay, so kind of important that everybody's on the same page. Right, your project teams, you're coming together right now to discuss what you want to do, what technologies you want to use, what frameworks you want to use, and you're all coming together to use a common paradigm. Right, so that's kind of what we're trying to get at here. So now, software engineering, where do you, the software engineering software engineer fit in? Consider it mainly that we're going to do applied computer science. So you're taking everything you're learning in your other classes and applying it to real world problems. Here you're going to have a customer, you're going to have clients and users, you'll have project managers. Basically, you're taking all of this theoretical underpinning that you're getting in your programming classes and all your other ones, and let's make a real package of software to release. Okay, along with many other things. Again, development is one tiny little piece of that puzzle. So this is basically reiterating what I just said. We have computer science over here, and we have a customer with a problem over here. The software engineer is going to take everything this person learns out of computer science and synthesize it into some way to solve this customer's problem. And if you need a visual for customer, consider me your customer for your term projects, right? I have a problem in that I need each of your teams to give me something cool, something interesting, right? My problem is very vague and it is very nebulous, but it is up to the software engineering teams to kind of whittle down what this is. Right? And you're getting the tools and techniques to solve this problem. So how have we been doing? Like I mentioned at the beginning, at the top here, we have many catastrophes that we've seen, right? The explosions, the loss of money, the loss of life, and all of that horrible stuff. We also have a lot of success stories. We wouldn't be where we are today without successful software engineering projects. We can talk to people on the International Space Station, right? We can talk to people across the globe. We can hold class on the internet. No matter how painful that may be, face-to-face is obviously usually better for most people. We have technologies and infrastructures in place that are created by engineers, right? So not just word processors or spreadsheets, which if you're using something like Google Cloud or Teams or 365 or anything like that, that kind of an engineering effort is pretty incredible in and of itself. But we have a ton of good stories of good use cases for where projects have gone right. And the issues you don't necessarily hear about those as often because they're not as, newsworthy, I suppose, but lots of good stories. Where software can go wrong is when we have bugs, when we have faults, things of this nature. So you all, I'm sure, have heard of bugs. Basically, we have two kind of common issues with software. We have faults. This tends to be when a human is in the loop and makes some kind of a mistake where, spoiler, never trust your users to do anything right. We're going to have errors because of that. We can also have failures, which are departures from your system. So if I tell my system I want it to perform in such and such and such a way, and it goes off and does something else, that's failure. It's departing from what I am anticipating. Probably a programming or implementation error, or some kind of interaction with another system, but it's still a problem for us to solve. Right, so your two most common factors that are going to lead to failure of some kind are going to be users and bugs. So just keep in mind, be wary of your users. I had a computer science professor when I was an undergrad. His favorite phrase was users are losers. So keep that in mind. I will be happy to repeat that over and over again. This is one of those slides where I'm going to kind of skip through it because we already talked about Therac. We've talked about situations where lots of money has been lost. For instance, the IRS had a problem as well, and there were software failures in that regard as well. Don't need to beat that one to death, but we have to be careful, obviously. The important thing to consider from a software engineering perspective, though, is who is considering your system to be successful or not. When you're no longer just a programmer, when you're a software engineer, you have to consider other people's viewpoints of what good software means. So transcendental view means that we have a good project or a good product, but we can't really say why it's good, which is somewhat bad, right? You should have good metrics for what constitutes good software. But you have your user's view. User loves your app. They're going to rate it high in the Play Store or the Apple Store or whatever, and they're just happy that it works. But we also have our manufacturer's view, where your quality there is going to be, was it programmed correctly? Can we spit out 500,000 units with this software and everybody's happy? We also have our value-based view and our product view. So how well does our product sell? How well can we market it? What's our return on investment? Right? All of these kind of budgetary concerns, which you don't think of as just a normal programmer. But when you get into the real world, terms like return on investment and breaking even and that kind of thing really come into play. We are not necessarily going to get too deep into the weeds with those kind of calculations. You can basically extrapolate based on how much I have to pay all my software engineers, my testers, my customer center people. So everybody that goes into a project, plus all the development time, plus all of your different kind of money sinks, they all go into a set of formulas. Those formulas will tell you, okay, at which year in the project are we going to start making money on this thing? Because there's like no benefit at the beginning. It's all sunk costs, unless you have clients paying you to do that. So that is the deep dark side of software engineering. We're not going to get into that too much, but it is there and be aware of that, basically. All right, so a good software engineer has a strategy for good quality of software, right? So this goes back to our ethics from last time. Make sure that you're doing the best that you can, but keep in mind that you have to produce a good quality product, okay? So in terms of the product, the process itself, and your business environment, basically all of these different aspects kind of go together. The term quality is meaningless unless you have metrics for saying what quality is, and we'll be getting to that. Get my little red O off the screen. Sorry for all the hammering on the T here, but I seem to be losing my voice today. Question for all of you in the chat. So, does anybody know what a stakeholder is? So we've got many different people and different roles that we'll be talking about. They're all stakeholders. Can anybody take a stab at what that might be? No. Honest answer. I like that. Someone who owns part of your company or project, basically. Kind of getting there. Owning part of the company is a bit... they would be a stakeholder, I agree. So, good guesses. A stakeholder is going to be somebody who has any type of, I don't want to use the term investment, but any type of connection to a project. Right, so that's kind of a good back answer. Vested interest in the products. There you go. So this will be your developer, this will be your quality person, your testers, your users, project managers, company owners, anybody who is tied to this project. A vested interest in success is basically a good way to describe it, right? My project will impact them in some way, whether it's quarterly reviews, whether it's money coming in, whether it's part of your job, right? So any way you're tied to that. The thing to consider is that every stakeholder is going to have a different perspective and a different view on success, right? So if I'm a software tester, my interest is that the test cases are passing, that we're not seeing any bugs, and that anytime I find something, I can report that back to the developers and that gets fixed, right? So that's the tester's interest. Quality, the quality people are making sure that we are passing our process, that we are basically passing all of our audits and things of that nature. So they want to make sure we're in line with that, right? So every stakeholder is going to have to be satisfied in some way. So designers, maintainers, users, everybody's going to have a different viewpoint here. And what I keep talking about with this idea of a process, have any of you heard of the different software development processes, the development life cycle? Like there's the waterfall model, there's agile, there are the rapid development, like the prototyping models. Anybody hear of those at all? I guess I should say if you have worked in industry at all, like if you've ever had an internship or a job, you probably have interacted with it in some way. No, that's good. They are basically, so a process, and we're going to get into this more next time, like the different types. They are a rigorous set of steps you will follow from project start to completion through maintenance of what you have to do. When do you define requirements? When do you define test cases? When do you implement? When do you talk with customers and clients and that kind of thing? And the interesting thing is that as we're modeling our software process, and these are different software process models, depending on your situation, you could have a different process, right? I have students in other classes where their requirements for what their project is will change daily. So I'm writing code, and all of a sudden I get a new requirement from my customer, and that has to be implemented by tomorrow. You don't have time to go through the entire iterative process with some of the other models, but something fast and lightweight would be more appropriate for that. Whereas environments where you have a lot of well-defined requirements and there's not a lot of change, you can afford to have maybe a slower model. But we'll be getting into that later on. Point is that all of these processes, this is a formalization that you have to follow. And what we're going to see is that implementation is like one tiny bullet point in this whole process. I already talked about this a little bit. Return on investment. Keep this in mind that anything you develop can have a business implication. So as you specify your projects, make sure that you're not needlessly spending, needlessly staffing. There's a lot of basically trade-offs when you're creating a project. These kinds of things tend to be more if you're going the systems analyst route or again more of a business type of route, but it's something that you may have to consider as a pure software engineer. Okay, so who is doing the software engineering? I can guarantee that 99% of you, if not more, are going to go look for a job if you don't have one, and the term that will be the description is software engineer. And what that is going to be taken to mean in industry is you know how to program. But software engineering as a whole is not just programming, it is working with other people, which you're all being forced to do in your teams, which I'm sure everybody loves. I know I did as a student. But you also have to go through the process of doing the models, doing the requirements, helping with testing, things of that nature. So you're basically a well-rounded programmer, I guess, and ethical and everything that goes with that. So again, some lovely clip art here, just to give you an idea of what a project may look like. And these are your stakeholders, again, at a very minimal level. You're going to have your customer, somebody who sponsors the development of the system, somebody upfronts the costs for you, basically. This could be your company if they want to design a product, could be an external company if you're being contracted, basically somebody who needs a project done. That's your customer. The developer is going to be the software engineer, right? They make the system, they code it. You'll have people who are not necessarily the developers who will help with the requirements and the test cases and the maintenance and all that fun stuff. So this is going to be your software engineer, kind of a nebulous bubble here. And then you have your users. Your users are not necessarily your customers, right? So if I am, oh, what's a good uh, game company like Hapu, if you're Risk of Rain or anything like that, they want a game. The users are the people playing the game, right? It's not necessarily the company itself. So there can be a clear distinction between customer and user. User is just the person who pays for it after it's been released. But their feedback's going to matter as well. All right, makes sense so far? Kind of high level, let's formalize what software engineering actually is kind of topics. Nobody got what this picture was in my morning class. Anybody here in the afternoon get it? If not, additional homework is to go look up internet history. This is one of the infamous strong bad emails, and I would do a GIF here, but it's kind of seizure inducing. Is that a cat with uranium? I think it is some kind of cat with a glow stick, basically. But yeah. Homework, go look up what my formative times on the internet were, I suppose. Cat with uranium. That's a good description. I've heard of strong bad. There you go. It's probably circa 2002, 2003. Old-timey stuff on the internet. Loaf of bread. Oh, loafing. Nice. I could see that. All right. So, software engineering in terms of a system as a whole. We are going to have to scope out what our system actually is. So it's very, very important to figure out where the boundaries of your system are. And if the only thing you've ever had is intro to Java, you're going to be aware that you're going to have like a Java class, and that is your system boundary, right? anything going into or out of this class has to be considered, whether it's data coming in, data that you're returning to a superclass somewhere else or a calling class. Basically, we have to figure out where the boundaries are, what the objects and methods are, and every kind of interaction the system can have. Okay, so there are kind of four main parts of a system. We have activities and objects. So activities are basically your methods. So what is the system going to be doing? Objects are, well, we should hopefully know the term object, but basically it is some thing in your system, some entity. And, could be a structure, a class, or anything like that. Bruh. Nice. Um, Basically, it's something in your system. Relationships. This is how your system connects to other systems, right? So you're going to define what it means for class A to interact with class B, what it means for data to be going in and out from these different classes, so on and so forth. So basically, we're going to have some kind of way to describe these interactions. And then the boundary, just where does your system start and end? So I talked about this morning. It's kind of an interesting view of what a system would look like. So we've been talking about in terms of computing. Consider a human respiratory system. This is also a great example of a system. Your boundary here is going to be your nose, your lungs, your mouth, your larynx, all of this fun stuff. So this is where air is going in and out, right? Activities are going to be the jobs it does. Do you breathe in? Do you breathe out? Do you take the oxygen out of the air you're breathing? Do you exhale carbon dioxide, right? So these are your activities. The entities are going to be the things in this system. So this is your oxygen. This is your nose, your mouth. Um, Consider entities from your, again, basic Java stuff. Your dog is a animal. Your cat is a animal. Your rat is a animal. These are all entities. What defines what they do are the activities. And the boundary is where this animal or respiratory system stops. Let's take this towards the computing side of things, all right? So here is a physical paycheck creator. We have some aspects here. So we have a computer, we have a mailroom. If you want to go the direct deposit route, this could all be electronic. So this is your bank account. This is still the computer. This could be like your payroll person's computer. They go in to the payroll system. System boundary is me entering into this. And inside there, we're going to have some activities, some entities that have to be happening here. All right, so first thing, let's validate the dates. Let's enter the date as an object. Let's do calculations based on your weekly take-home and taxes and all that fun stuff to consider. Then, if it's a physical copy, we have to print it. If it's an electronic copy, we have to send off that wire to the bank. The point is, this system, it has a boundary, it has data coming in, it has data going out, and it has data being transferred all throughout the internal system. All of these things are what we're modeling in software engineering, right? But the nice thing for us here is that if we're creating a system, we basically mainly care about the internals here. We have to model the outside world to make sure we know what our environment is, but that's sometimes out of our control. So we at least have to model what we know. It's possible to have systems of systems. It's possible to have related systems, systems that depend on each other, systems that comprise multiple systems. So for instance, here's kind of an oniony model of a data collection system. So think of this like an IoT, you got sensors spread around all over the place. We have created this engineered system. Well, crap, we just are collecting data. We also need something to manage calculating any metrics from that data. Well, in order to support that, we need a way to communicate with these things. All right, so how does your sensor motes or a little tiny Arduino or Raspberry Pi or microbit sitting outside in a little box, how does that talk to your main server? Then how do you even get that data or make reports based on it? So the point is that these systems can be related and they can talk to each other and depend on each other. But all of these dependencies are things that we're going to have to consider here, right? So what I've got here is a list of the typical activities you will have as a software engineer. We have to write our requirements. These are going to be written in natural language, right? So they will be English, or your language of preference, depending on where you're at. They will be very specific. They will have hard metrics with them. They are very rigorously defined, right? They're specifying exactly what your system does. If you are going a more agile route, these might be user stories, but those are then going to be a little bit more flexible and not as specific. We're going to have our various levels of design where we figure out how our system is put together. Again, what the dependencies are and all of the interactions and things of that nature. We're going to do unit testing where we test our functions. We'll do integration testing where we test the system as a whole, or what happens when we compose multiple pieces together of our system. We'll look at the system itself as a whole, look at the system after it's been delivered, and then we're going to maintain it over time. Right? I skipped writing the programs. This is one bullet out of many. Again, implementation is the mechanically easy part. If you've done all the hard mental load at all these various aspects, right? What's the design? What are the requirements? What are our tests we're going to run? All of the thinking, the programming is just sitting down and doing the work, right? This is the mental part. This is the hardest part of the process to me. If you're just learning programming or if you're just getting into it, honestly, the programming probably sounds really hard as well. But again, it's something that you can technically pick up pretty quickly. The hard part, again, is thinking about what we have to be doing here. Any questions so far? And I've got about a little under 10 minutes before we get into our demo. If not, let's talk about who is part of our team. All right, so you consider yourselves probably more or less programmers, I would imagine. Consider that we're also going to have people on our team who have to design the system, people who are good with working with other people. So our requirements analysts, talking to the customer and getting out of them what they want. People who are going to be testing. So testers should not be the programmers. Right? We saw this with Therac. It should be separate people, separate groups, no bias in the software process, right? You're also going to have people who can train your clients, people who will be helping maintain the software. Configuration management people, making sure all of your software artifacts, all of your documents are all kept and maintained, basically. Librarians you may have too. These are going to be people on your team who maintain all of the documentation, the user guides, the requirements, all of this kind of stuff. Keeping in mind that there may be some crosstalk between these different roles, right? You might help with requirements design. You might help with writing initial test cases or writing training manuals since you're the expert in this. So it just depends on where you fit in your company and what the structure is, right? And again, this is just a clip-arty view of what the system process kind of looks like. Your analysts, your programmers, so on and so forth. There's a chance that you have some kind of an impact on any of these, right? It just depends on your layout. If you're a one-man team, you're going to be doing a lot of this. But hopefully you always get other people looking over your shoulder to make sure that you don't get into a biased state, right? I'm going to kind of start skipping through this a little bit since we only have about 5 minutes before we do demo time. Basically, the things to consider is that things are always changing in software. So this is a well-known 7 key factors of change for software engineering. The things you have to take out of this are that anytime a new paradigm or a new technology is introduced, it becomes a problem for the software engineer, right? Since the 70s, these were the changes that were problematic. Desktops are introduced, right? We're no longer dealing with mainframes where we have one nice big machine to deal with. Now we have hundreds. Object-oriented was a step ahead. Figuring out when to get your product into the market, dealing with networking problems and other people, handling user interfaces, different economic policies, Problems with waterfall. This will become apparent next time, but the ancient classic software development process has some problems with it. Again, it's not super flexible. These are 7 things that have changed since the 70s. It is now 2020. We now have cloud computing. We have quantum computing. We have um, IoT and all kinds of new acronyms that are out there. These all impact software engineering, right? Great example here. Let's talk about cybersecurity. How the heck are you going to encrypt your data in cybersecurity with the ability for qubits to defeat, was it the AES, or one of the most common encryption protocols was broken with quantum computing a few months back. If you have no idea what I'm talking about, basically look into quantum computing. It's going to be very, very interesting for how it impacts lots of different software domains. Um, Basically renders a lot of cybersecurity obsolete. Um, so we have to deal with change is kind of the point. And how do we handle that with software engineering? We go the object-oriented route. We abstract things, we generalize, we try to reuse our code. We make sure that we have as rigorous of a process as possible. And I'm going to kind of skip through some of these slides because a lot of it is, I'm reiterating what the beginnings are saying. That's kind of nicely wrapping things up. The only thing I want to hammer on here is that in software engineering, you know, whether you're going object-oriented, whether you're doing enterprise software or a desktop app or a phone app, it doesn't matter. At the end of the day, in software engineering, there are going to be 2 sides to how you go about your job. You can go the empirical route, which is here on the left side. So this kind of column here, this is where you deal with real world data. This is where you put your system out in the wild and see how it reacts. Okay. I'm not necessarily talking like early access or anything like that, where you put out an unfinished version. I'm more so saying you take your program you've created, you've checked it as much as possible, and you test it in as many different real world situations as possible, right? You're getting real environmental data from this. The other side is the formal world. So this is where you use mathematical proofs to try and verify that your software will work as expected. If you've had to do mathematical proofs in like calc or any classes like that, it's very similar to that. The only difference is you're probably doing it in a more logic-based language, right? Something like linear temporal logic, if you know what that term is. But basically, you have a simulation of your system, and you have a rigorous mathematical proof that's written out for how it will respond. Too long didn't bother to listen to the boring old guy on Twitch is that this side is more mathematically rigorous, but less real world. This side has no real mathematical formal reassurance that your system will work as expected, but you have a ton of real world data backing you up that it does. So it's a huge trade-off with which side you're going to do most of your efforts in. Does that kind of make sense? This kind of schism here. Honestly, if there was a great bridge where you could spend a ton of time formally modeling things out and then applying it in the real world to back up all of your proofs, that'd be great. Unfortunately, there's not always a ton of time to invest in both. You kind of get a light look at one and a light look at the other. So with that, I'm hearing Discord bleep at me, so I'm hoping there's not something horrible going on. Okay. What I would like what I would like to do now, and again, like the rest of this is let's talk about the Ariana 5 explosion, which we don't want to talk about. Monday, we'll talk about the process models that are out there, to some of the different development paradigms. But what I wanted to do is get you into looking at Git and GitHub. So what I will do is now show you this, and feel free to ask questions in the chat as we go, because that's gonna help hopefully you. And then I can do my little meme there to get us going here. So this is GitHub. If you have never ever seen GitHub before or have any idea what this is for us going to basically be way to manage all of your source code and all of your documentation for your teams. That's what we're going to use it for. This is a base repository that I've created for all of your teams to use. So we're going to have a location for all of your artifacts. These are all your models, your documents, things of that nature. Place to put meeting minutes, place to put your source code, your tests that you're going to write, and your websites. All in one place. And then this README file, this is basically going to be your term project report when you're done. I've got some basic things in here, but it's going to be probably changed later on based on what you need to deliver. So this is the base thing. So what one of your teammates will do is they're going to fork it, and they're going to bring it into their account. All right, so I'm going to go ahead and fork this. That means that I'm taking this repository and I'm dumping it into my user account. So now I have a copy of this thing. You get a little confirmation up here. I don't like the name base, so I'm going to go ahead and change that. So I'm going to go into settings, make sure you look through some of these links that are around here. So I don't want to call this base, let's call this Frederick's CIS350 term project. Rename. The website is a very nice thing to deal with, I will mention. Okay, so I have this. It's GPL licensed as well, so that means it's open source. Feel free to pick the license of your choosing. I'm going to copy this URL and early view at your lab manual there. I'm going to go into my terminal. Now again, everybody has a different computer, I'm sure. I will be using terminal commands for Git. I will give you examples in your lab manual of terminal commands. This will work in Ubuntu for Windows or any Linux on Windows where Git is a command. There's also Git for Windows. It's 141. Yeah, so this is what we're doing now, by the way. Not sure if there's a delay or not. So if you decide to go the graphical client route, you're more going to be on your own to what else is out there, because I'm going to do all of my demos in the terminal here. So it's pretty easy once you get used to it. So I've forked this repo into my account, and what your teams are going to do is one person will fork it, and then they will invite all the other users to contribute to that project, is the way it should work out. I need to pull a local copy down. So I'm going to run git clone and then the URL to this project, right? So I'm going to clone it. And what this is doing is it's taking a copy of the remote repository. So this is a remote, meaning it's somewhere else. And it's making a local repository on my computer. This is the thing with Git. It's distributed. You have a local copy and a remote copy. How this will work is that you clone it down, you pull any new changes. Oh, you don't clone it down every time, but you're going to pull any changes every time. You're going to basically make your changes locally, and then you're going to sync them with your remote. And once your changes go up to the remote, any of your teammates can also pull that down, which is why this becomes nice. You'll be doing things like this in industry, whether it's Git or SVN or some other thing. Bitbucket's another example. You'll be using something like this. I can pretty much guarantee it if you become a software engineer. So I have a local copy. I see it right here. So ls is my list files. I go into this directory, clear everything out, and here are the files from that remote repository and directories. All right. So I've made all my changes here. I've pulled down, I pulled down the repo. What you're going to try to do, what I would encourage you to do every time is to run this git pull command. This will pull any new changes down to your computer. So if one of your teammates changes something, a git pull will bring that down locally. How does the terminal know git commands? Is it built in? It depends on your terminal. I'm using Ubuntu, which is a Debian variant, so I think it's sudo apt to install git if you don't have it. So I already have it. But basically, there's many different methods you can get for installing it in the terminal. There's PowerShell git commands too if you'd rather use that. So I've done a git pull, and now what I want to do is update my README file. So I'm going to use Vim. It's a Linux text editor, my favorite one out of all of them. Frederick's term project, the best around. Project description. This is my project. How neat. Creativity, plus plus. Go, go, go. All right, so I made my changes. Should mention text files in Git, at least on GitHub. It knows how to read Markdown files, so this is Markdown. If you've ever done anything with Markdown on the internet, pounds are going to be headings. Asterisks are going to give you bullet points. Is basically your Discord formatting language is actually Markdown, if you're not aware. Point is, I have made a change. All right, so let's also create a new file. So touch just creates an empty file, basically. So I've updated README, I created new file, and if I run git status, I see changes. So git status tells you where your local repository is at. readme.md is modified, new file was added. Okay. What I have to do now is I have to stage things. So I want to do git add, and I can either go file by file or I can just do everything. So I'm going to say just do everything. So git add dot, git add asterisk works as well. What has changed since then is that before these were not staged. Now these are staged to be committed. All right, so they're green in my terminal. This may differ on your terminal. So Git now knows about these files. If I want to commit them, I should give it a useful message. And what committing means is that I'm taking these changes and I'm committing them to my local repository. So if for some reason the files get blown away, Git will know about this commit. So I updated README with project title. Okay, so I created a commit. Anytime I want to look at this particular commit, and a commit is basically a piece of history for this repository, I will see this message for whatever files were updated. Still local, I should mention that. If I go back to this web page for my project and I refresh, nothing has changed, right? It's only on my local copy. The only time that the remote repository gets updated is when you push. So git push. That's all you have to do. If you have multiple branches and things like that, like your homework due tonight had, you're going to have to do something a little bit different. You have to push it to the correct branch and all that fun stuff. Here, if you have a single branch, just standard git push is fine. It's going to ask you for your GitHub account. So it's still linked to my Oakland email. Oops, typed that in wrong. Git push. Don't talk while typing out passwords that you can't see. All right, so changes have been pushed. We also see part of our commit ID. So now when I go back here, I'm going to refresh. I now see my changes. New files there, README has been updated. This all happens very, very quickly. If you click this commits message here, we actually can see the different commits. So if you need to access a particular version in your history, basically you have to check out a particular ID, right? So here, this is basically the change of what this particular commit is, right? So if you're not familiar with diff, this is basically diff in a nice, pretty format. This was added, this was added, this was added, this was subtracted, this was subtracted, things of that nature. Point is, all you really have to do is git pull, change your files, git add, git commit, git push. Pretty straightforward process. And your next lab manual will give you some hands-on practice with this. Can you resolve merge conflicts in the terminal? Absolutely. You can. I will give you the heads up. This is either a running joke on the internet or just the easy solution. If you start running into Git problems, oftentimes the easiest thing is just to copy your changed files and delete the repository locally and reclone it. That's kind of the cheating way of fixing merge conflicts, I suppose. So yeah, we have actually hit right on the nose 150. So software engineering, very, very useful. GitHub is what we'll be using for the term project, and your homework is due tonight. And your next lab manual will give you hands-on practice with this, not just a click these buttons and watch things happen. That was more so you understand what all the terms are. Anybody have any questions before I release you for the weekend? Before I can start adding whiskey to my hot beverages. Homework as in GitLab. Yes, so the homework is the part 1 GitLab, I believe it's called. Class sessions. Intro. Do. GitLab part 1. This is what's due. Yes. And again, if you're lost with what's due, there's this calendar here as well. So this should tell you GitLab part 1 is due. Anytime the Dragon of Light. Oh, I should mention too, I did start tracking who is linked to what account, so hopefully I should start realizing who is who. Again, if you haven't joined a project team, please drop a message in Discord. I created a unaffiliated page where if you don't know what team you want to join, just drop your info in there, and hopefully that's helpful. Otherwise, by probably tonight, tomorrow, I'll just drop you on a project team that I think would work for you. All right. Unless anybody has any other questions, I will end the stream and see you all on Monday. Have a great weekend. Gotta end with something appropriate though, I think, right? Come on, better TTV load. There we go. Party time. Have a great weekend. Cat Jam. I like Cat Jam. That's a good one too. It's almost Halloween, so the spooky, scary skeletons gotta start going. And if there's any unintended innuendos with any of these, I'm not aware of them yet. I'm not ashamed to admit that. So it's Friday. There we go. All right, bye everybody.